So I've still got work to do on the power supply, but I have also I made myself start designing the cable tester. And I want to hopefully do that over the Christmas holidays. And that means I need to order the parts soon, so I need to make sure all the tricky parts to get, I know what they should be. So one thing I need to do, which I'll show in this video, is among other things, which is to make sure that is my pen working? I don't think this is the resistor that limits the current into the LEDs in these. Well, you can call them SSRs, but the manufacturer calls them photo MOS relays. So I want this to be. Can I show the? Where am I looking? Let's just make sure it's not the right picture. I gotta do that again. So I've still got work to do on the power supply, but I made myself start redesigning or designing the cable tester. The idea of the cable tester is to use effectively solid state relays on two boards connected by Wi-Fi, so that the solid state relays can be used to manipulate the connections, so you can find out which wires are connected to each other wires, if they've got shorts or if they've got voltages you didn't know about. I wanted to do this over the Christmas holidays, but what I need to do is to make sure I've ordered all the parts which might be difficult to get or which might not be in my inventory. Because it's in the design, there's so many relays I want to use. I need to use a lot of resistors to limit the current through the LEDs on the relays. Oops. So they're not called SSRs by the manufacturer. They're called photo MOS relays. So they work. There's an internal LED and then light sensitive FETs, I think. So if you light the LED up with up to about 3 milliamps, then the resistance of this between these two pins drops to about 25 ohms. But my original, this circuit is not the final design. This is just the test board that I've made because I'd never used these relays before, these photo MOS relays, so I didn't understand them properly. I wasn't trusting my reading of the data sheets. I'm going to lose my voice. So I think this resistance is too low, and I think from calculations, I think it should be, if I can get this to work, I think it should be 1.5k. So what I'm going to do is put a potentiometer in place of this. I'd already put pins on the board, so I can just plug that in and measure this current. So which WO, so that's this one. And then I want to make sure that the resistance of all of the relays that are turned on is roughly 25 ohms. So at the moment I've got 5 volts here, ground, and this relay's on, I think this relay, this relay. So there's 4. So there should be 4 times 25 ohms, and 1 times 100 ohms, which is that at the moment, because I've put that link in to put that link out. As I've bridged this. Whoops. Right. So if I turn off that, that's what it looks like turned off. Gonna go. I'm still coming to terms with how to video this and record it. Whoops. And I forgot to transition. So now you can see. So that's the test. That's the test bed. So it's turned off. So that's 1.5K. That's the bridge over the diode and the resistor, the 100 ohm resistor, and the diode's bridged by this. At the moment, so this, I'm just going to, that's my double adapter for board connection. So if I measure the resistance, so I've got 1.5K. So if I then turn this to voltage and plug this in instead of R3, hopefully okay, so that's plugged in instead of R3. It's working. So where is it? There. Now it's 1.5K, which is turning on this, and that's, so if I measure the voltage, once I turn this all on, not blow anything up, and I get 3.6, so 3.6, yes. I think I need a microphone that doesn't have to be carried around. So if I turn this back on and transition, so now I'm getting, what is it? It's a 3 point, whoa. 3.69 volts, which is over 3.69 divided by, it's early in the morning, 500 equals 24 milliamps. That's good. No, it's not right. 2.4, 2.5, 2.46 milliamps. What did I want to do? I want to, so that's good. So if I bring up the typical, so the typical on is 1.8, and the maximum is 3. Where's the abs for the absolute maximum is 50. Which, yeah, okay. So I want to get it reasonably close. I'm questioning whether I need to try. Yeah, maximum 25 degrees, 3 milliamps, 2.4. I might try something. Let's go back to so if I take out just need, it's a bit fiddly here. So if I power this up, not at the output of the gate, but directly to 5 volts, it should 3.8. So when it's 5 volts, it's my test if anything's burning. Nope. 3.8 volts. So now I come back. So 2.5 milliamps. That's fine, I think. So now I just want to measure the voltage across. I can't draw that, which will tell me so this is bridged, those are bridged. So if I measure this current, I can find out what the resistance of all 4 of these is. So I'll do that now. Now, the voltage across here. Oh, come on. 2.4 volts, which is 24 milliamps. 2.4 volts. 2.4846 divided by 100. Yeah, 24.8 milliamps. 25 milliamps. Okay. So 24.8 milliamps. Let me just go back here. So we got, what is it? So we got 24. Oh, come on. 24.8 milliamps. So, and it's through the 100 ohm. So that's 5 volts. Oh, come on. Why does it do that? I think. So, so 5 volts. Oh, my brain is not working this morning. The total resistance is 5 volts on 24.8 milliamp. Oh man, 24 point. This morning I'm not thinking right. 24.8. So it's 201 ohms. Is it? Oh, whoops. ohms, 201.6. So the minus 100 is 101.6, and then 4 relays, so divided by 4. Yes, so it's pretty clearly, I don't really need to work that out, but 25.4 ohms each. 25.4 ohms, which is good. So the maximum, so we've turned them, we're pretty much drawing up near their maximum load. I think, where's the load? Oh, I know, we're not anywhere near. I don't understand what this means. 120 milliamps peak AC. Okay, I'm not sure exactly about this. So that's probably peak. So if I convert, I don't know what I'm talking about. If I converted that to RMS, that'd probably be the same as the DC. I think, what's that? Let me just give it good. Is that 0.12 times? Let's have a look. Yeah, I just checked. Yeah, it's 0.707, so it's about 80. So if it's peak 0.12, if it's 0.12 amps peak current, then it's 84.8 roughly, 84 milliamps. Whoa, 84.8 milliamps RMS. So that is all within the limits of the devices, I think. I mean, they're currently, because I'm using 768 ohms, the LED current's probably a little bit on the high side, but not, doesn't breach the maximum limit in this test board. But the real board will be within less than 3 milliamps, so that's going to work, hopefully. In any case, this is the first of quite a number, because I'm still in the process of designing it. So at the moment, it's mostly I2C, so I'm using I2C bus extenders so that the boards will basically be I2C peripherals. So, and so there has to be 2 of these relays now. That's the correct designation, AQY280H. But so you effectively don't need to know what the polarity of the wiring is. You just you've got control of both ends. Use a EMOS D1 Mini as the control, which has got Wi-Fi, so they can communicate to each other. And there's the possibility of putting a test voltage down the line. Well, it has to be that way. And using this is a programmable, I think that's the one, the programmable frequency generator. I want to be able to send various frequencies down. So that thing can be, I think, from 1 kilohertz to 86 megahertz, which is overkill, but and they cost about $10 each. But if it's on the board, maybe not the first version of the software might not take into account, but if I can have it in there, it'll mean that at some point you can make a different kind of non-contact sensor and trace the wiring that way. So effectively the whole point is you have this app, a web page. The EMOS has got a web page as a primary and a secondary device. You would effectively log into the primary device, and then you've got a web page which has the display of the wiring connections that it's found, the state of the wiring, and you can also do control it. So you could then say, well, the hope is, I haven't done any of this yet, you can say send X frequency down wire 5, and then you let that sit there, and then you use a detector to find out where that wire is. So I just wanted to try to do a better explanation of the concept. So here goes. So there's two devices with, at the moment, 8 connectors. They're completely independent, but they talk over Wi-Fi. And then there's a mobile phone will connect to the primary. This is the primary, say. And this is the secondary. So you plug connectors into wires, which you don't know if they've got shorts or breaks. You don't know which one's connected to the other one. So 8 wires. And and then you power this up and connect the mobile phone to the web browser on the primary. And so it goes through a sequence of actions. The first thing it does is try to figure out if there's any voltage on any combination of the wires on each end. If it finds that, then it stops. Particularly, and if it finds a high voltage, like a dangerous voltage, then it should flash and have a buzzer. So once that's done and there is no voltages, then it starts applying voltages on one side to all the pairs of wires, and then checking all the pairs of wires to see if it can find that voltage. And by a process of elimination, then it should be able to find out which wires go to which other wires, or if there's a break, or if there's a short. That's the idea. I need to think about this more just to see if it will work. On each end it's effectively a low impedance voltmeter, so that it drives a bit of current, tens of milliamps through these wires, so you don't get like phantom readings. And given that I can use, I think, a 12-bit A to D, I should be able to get a pretty accurate. Well, I should be able to tell the difference between wires. I'm not sure if I need to know the absolute resistance of the wires, but I can at least do good comparisons. I think there will be a calibration stage where you just connect the thing together with the known wires, set it to calibrate, and then it figures out its internal differences, and then you go ahead and connect it to the wire under test, or the cable under test. So my thought just then is that it may need some way of saving calibration parameters. The other thing which I realized the other day is that it would be a good idea to, what's going on here, to have an oscillator in here too, which you can apply to any one of the wires, so that you could say apply a frequency here, and then you could use another detector, which I have no idea how to make yet, to detect the RF radiation. So if all else fails, like you don't know, that may only work, that may be only useful if you can use one of these at once. I know these tools exist, but then you can apply a frequency to any of the wires and then use this other detector non-contact detector to detect where that frequency comes out, where the wire goes. So I think I've repeated myself a little bit, but that's the concept is to connect these devices on the either end of a long cable where you can't get a multimeter. They're long enough that you can't get a multimeter to buzz the wiring. Say a network cable, for instance. And then you run this, and then you can determine whether it's good or bad, or other cables where you don't know necessarily which one connects, or if you've made a mistake, or if you've made a mistake in a connection, so you've got a high impedance. And that's the concept. I hope that makes sense. I'm going to lose my voice any minute. So I'm still in the process. As I've already shown in this video, I've got the circuit to a degree I think is okay. I need to go through some scenarios to make sure that the ideas that I've had how to do this testing will work. So basically, I need to as I mentioned, buy the parts that I think I will need before I finalize the designs, because there could be delays on purchase. After I purchase, there could be back orders, and I want to do this over the Christmas period. And yeah, that's the main thing that I need to do. And I need to get a board designed which has got some kinds of configuration. So I'll use through-hole components, for instance, mostly, because I can swap them out more easily. Because I may not be quite sure of all the component values. I hope that makes sense, and thanks for watching.